Okay, hello everyone and good afternoon. Uh, Thank you for joining me today. But first of all, let me remind you if for some reasons I have several typos and I'm just working on with the slide quite late. Okay. Okay. Actually, half of this slide on geometric quantum complexity of bosonic oscillator systems have been discussed them together with Chong and Umar the other day. But today, maybe I can go through again from the beginning and then start to emphasize some important parts from the paper. Okay, so the paper I have already share it in the groups. All right. So this is the paper written by these three person. I'm not sure if it's already published. Maybe Chong can help me out to verify later on. Um, the outline is they discuss on the notions of quantum complexity, measure the difficulty of generating a complex task by emphasizing successive simple operations, and then they emphasize on the geometrical approach method on determining quantum complexity. Uh, so the aim would be looking at the complexity on the generators or on the operators, in this case, the unitary operators, um, where they can also compute the complexity bound, okay? And they have provided several examples using the method. Just an introductions from Nelson's formulations, okay, how they determine the complexity of specific quantum states, looking at minimal circuit size necessary to implement n-qubit unitary operations. They mention some of the drawback does not provide a comprehensive understanding of the complexity associated with the quantum process in general. So they're just looking at the minimum of circuit size. Okay. A bit on gate complexity. So we have the following equations where you have the target state and reference state, and you have this unitary target operator. U target is the unitary operator that realize this transformation. How about counting gates? Okay, this is a constructions of quantum circuit by building it out of elementary operations that synthesize the unitary gate. So you can have a like a successive unitary operator acting on reference state. So for gate complexity, they made it such as the number of quantum gates used in the optimal circuit that implements the desired target unitary within some level of accuracy. Um, this is some drawbacks of the gate complexity, but what I want to discuss in brief is on Nelson's geometrical approach to quantum complexity. So they mentions on connections between quantum complexity with differential geometry, how they determine the quantum complexity of unitary operations. That is closely related to the problem of finding minimal length geodesics in certain curve geometry. So we should assume having some geodesic equations. There's a tool to bound the value of gate complexity, and the complexity U, what they will compute is the length of the minimal geodesic on the unitary group manifold joining the identity to U. So maybe in detail, this have to be read further. The aim is to compute the complexity of an operator. So this is the main objective, where they provide a complexity bound of several operators. So let's look at some important features and definitions. So they use the Lie algebra generated by all operators, easy and hard ones, that can be exponentiated to a Lie group. They have some hardness coefficients where what they call the penalty factor matrix, denoted by G with Ij. Then they have the distance on the unitary space using this rule. So you have some generators O respect to I. And then they have the U point on the manifold. So U point here is the unitary target. And then the trace is taken in the matrix representations. But the main also determine the geodesics on the Lie groups equipped with right invariant matrix. In a way, they are using Euler, solving Euler-Arnold equation with boundary conditions. So these boundary conditions respect to the unitary target boundary conditions. So there are two parts over here. We're going to look at Euler-Arnold equations. So this also remind me of what H.E. Brun previous works on what they call Lex equations. So in general, from this paper, we can say that we have 8 steps to compute complexity of an operator. So you identify a basis of the generators that form a closed commutator algebra and hence specify a Lie group. The commutators of generators determine the structure constant. So sometimes they call this the frequency. Okay. So for the commutators, you solve the Euler-Arnold equations to get the set of geodesics. VIS corresponding Lie groups using the structure constants from the commutators of generators using equation 1. So the structure constant over here is F, okay, this one, and V here actually is the tangent vectors. So the structure constant is you get it from the linear from the commutator algebra given by equation 2. All right. So like I said, this is the geodesic equations given by equation 3. So you are trying to solve differentiating U. So U is the unitary target over some functions of S with this, okay? So the third step, consider generic elements of the unitary group by exponentiating the sum of the generators characterized by S-dependent parameters. 4, you solve equation 3 using the generic element defined in the previous step for all solutions of the Euler-Arnold equation. So all solutions, this depends on how many structure constant that you produce. Okay, depends on the Lie algebra. Number 5, you can determine the equation satisfied by S-dependent parameters. This is the boundary conditions. So target S, this is a unitary target for S equals to 0 and S equals to 1. Number 6, ensure the geodesics characterized by those initial values reach the target. Fix the initial value of the components of the velocity. Then you can compute the length of the geodesics for all values of the initial tangent vector determined in the previous step with respect to the chosen right invariant metric. And then you can have the length of the minimal geodesic that can determine the complexity. So this also you can produce the complexity bound. All right. So from the paper, they start with the harmonic oscillator group. This is generated by 3 elements, QPE. So they have this commutative algebra 1, 2, 3, and additions. This harmonic oscillator group also can satisfy the following in terms of X and differential form with the identity operator. So this is the common operators like the position, momentum, Hamiltonian identity. So they are isomorphic to the Heisenberg algebra. So we follow the 8 steps. So I missed somewhere, but now we start to go to. Okay. Sorry. Sorry. All right. Then we go to step 2. You can compute the structure constants from 2. So from here, you can find the structure constant is given by the following. Okay. So this structure constant allows you to look for directions of geodesics in the HOS group given by the components of the Euler-Arnold equations. So HOS is the word I denote for harmonic oscillator. Okay. And then we compute how to verify the diagonal penalty, GIJ. Okay. So we have GIJ following the earlier equations on what is the name of the earlier one? Okay, I hope you remember the earlier part is the geodesic equations. The Euler-Arnold equations. So this is the Euler-Arnold equations. All right. So IJ here will take the generators that produce satisfy the commutator algebra. So you substitute accordingly and you produce 4 four types of this. Okay, to be detailed, we have to read properly the dummy and fixed index. So again, you refer to your Fijk here respect to EQP. So, and allow again your Euler-Arnold equations take this form. Okay, so if you fix I respect to H, P, Q, and E, so your J can vary either P and Q or Q and H or P and H accordingly. But for the case of EE, this means index IE and J none. So this part definitely give you 0. So you can proceed further. So that's why if you follow all these rules, okay, it's like a tensor. And then you end up with 4, 5, 6, 7. Okay, 4 types, 4 Euler-Arnold equations. Okay, so these structure constants, you will refer back to what you produce here. Next is you are taking a conical delta over GIG. Okay, so all these, the first scale factor here, scale multiplications of GHH, GPP, and all will give you 1. So you will have, if you substitute accordingly, then you will end up with equations 8 until 11. So this means that you have only 2 pair and another one just equals to 0. They call this decouple. Okay. So from the paper, there are several typo. I think I've discussed with Chong earlier. So there's 9 will have only negative sign. Negative, and you have only positive from equation 10. So what you're trying to solve here will be 9 and 10, but 8 and 11 can be solved, I think, very easily. Okay. Anyone suspect what is the solutions of 8? Anyone? So it will be just some constant. Okay. So you have 8 and 11 because whatever give you, so it give you some constant, some using new H and new E. So you end up with 9 and 10. And since they are constant, so you just substitute accordingly to 9 and 10, and then you can have, in brief, this one, these two terms respect to GPP and GQQ. So you have like 2 sets of linear equations having in terms of differential form. So up until here, what I do, let's say you let y equals to VQ, x equals to VP, and you set the constant gamma. So you can have the solutions to your VP, VQ accordingly like the following. Okay. So if you have, so this is nice because you have plus minus one of them. Okay. So I think this is just mathematics. You can just substitute. Okay, you try to differentiate one time and then you substitute in another equations, and in the end you end up with trying to find the roots. So you have the complex roots, so you end up with the general solutions of this part. C1 cos S gamma, C2 sine S gamma. Your gamma is again VE plus VH. So this is different from the paper. The paper have minus signs. Okay, so we have plus sign. And then you can also find the solutions for Y is given by those. Okay, I think this one I have checked. So that is the solutions to the Euler-Arnold equations. Then you can look at the complexity bound. So you have all the, by right, you have all the tangent vectors now along all geodesics in the HOS group. So the constant nu I determine the magnitude of the velocity vectors at S0. You can write down the length of the resulting curve or the complexity bound. I did not put this earlier in the slide, okay, but from the paper, you do have that, where it is given by equations 15. So all these are the magnitude, okay. All right. The paper go further on looking at Euler-Arnold equations and its solutions. Now we are going to look at the generators that characterize the HOS group with commutators as the earlier. Then the group elements is given by US. So you have all the 4 generators. Okay. S is the parameter along a curve that will be required to be the geodesic. And then if you solve equation 3, so equations 3 is the geodesic equations. Okay, so if you're differentiating U over S, so that's why you have this alpha, because your alpha here is respect to S. So that's where alpha prime here. Oh, sorry, this is typo. So d alpha ds. Okay, and then using the commutator algebra with the structure constant, you can write down your u as exponential of all the sum. Okay, let's see if I get it right. I'm afraid do we have the exponential of, is it exponential or without exponential? Let me check. Yes, you do have the exponential. So exponential of minus I with the sum of I from I up to the n unitary degenerators. Okay. So we substitute accordingly. So you have all the VI, and then you have US, and then the generator. Again, taking the Kronecker delta of the penalty matrix and the solutions from page slide 20 to 21 for the tangent vectors, for which you can compute your alpha I. Okay, because you can equate them both, okay, using 12 and 13. So you can have 4 sets of first derivative order of alpha respect to S. Okay. For example, maybe number 16 and number 19 is easy to solve. Okay, so you differentiate. We use separable solutions, integrate both sides. So you can have your alpha 1, of course, respect to S. So you have SV plus C1. So you have what we call this a constant of integration. Okay. Okay, so from the paper, you have other 4 parts. Okay, so you have C1, C2, C3, and C4. Okay, and then you can compute this, because this is integration of constant. You can compute them accordingly using the boundary conditions. Okay, this one I have not check it in detail. Okay, and I think it should work. Okay, so at the end you have your phi 1. Actually, I'm giving you phi 1 is just SVE, all right? And so C1 and C4, at least from 16 and 19, give you 0. And phi 2 and phi 3 have an extra 1 over VE, okay? They just managed to put it here. It's from page 12, okay? Maybe later on I will share the paper if you want to see them. Okay, so what's next? We look at the complexity of an operator. So somehow or other we have all the methods, okay, that we're going to use. So the second part is looking at the complexity of an operator. Actually, they produce several. So the first one, the author discussed on the displacement operator, for which the U target, you need to target that make this transformation from the target state to reference states is given by this form. Okay. The second one is the time evolution operator. They rewrite in terms of omega, where omega is related to the mass for harmonic oscillator, right? And then they also consider harmonic oscillator harmonic oscillator system with additional linear potential, for which they add second terms of the HOS lambda Q, where the unitary target now respect to T. Okay, if you compare with the time evolutions number 2, they're just having omega, and then this one in terms of T. They also look at the complexity of an operator if the geodesic equations for general frequencies, or in other words, if we try to look at generalized structure constant. Okay, so for example, they allow HQ having minus P over M, and then HP having those. Okay. Of course, you can modify the earlier Euler-Arnold equations accordingly. But in this case, it is more complex and difficult to solve due to you cannot decouple the Euler-Arnold equations. Okay. This also given in that page 14. Sorry, maybe page 17 after. Oh, sorry, page 18. But what else? You can also consider nonlinear potential. For example, if you change Q over here into Q square, all right? But this does not contain in the harmonic oscillator or Heisenberg algebra. But one can utilize the other algebra, SP symplectic algebra, SP2R. Okay, this is covered in section 4 from the paper, for which they can write other generators respect to P and Q and look at the structure constant and follow again all the rules of finding the unitary target accordingly. Yeah, I'm about to end. So what are they found? Okay, so from each of the complexity of the operators, they have the complexity bound of generators. For example, remember this is, so for the complexity bound of the displacement operator is given by, so once you find all the magnitude, so you follow these rules, okay, given by 20. For time evolutions operator, I have not gone through in detail this part, okay, but I just putting in the equations. So you have for time evolutions respect to two variable. For can I ask someone what is these notations?
I think it's a flow function.
Okay. Flow functions, all right. And then for harmonic oscillator group with additional linear potentials, you have an inequality respect to the complexity bound. Okay, sorry, I missed out. So I should have lambda here. There's a typo. So, but this one respect to three variables, okay? And they plot the complexity bound function respect to the parameter, okay? I didn't put it here. So that would be the end of my, but for the section 4 on more generalized other operator, they also have inverted harmonic oscillator. That one I have not covered, so I didn't put it here. So maybe later on can have a look and continue to do that. So that is the end of my talk. Thank you.
So I didn't really completely read the paper, but perhaps it is mentioned in the paper, but perhaps I missed it. Do you know what is your physical kind of an interpretation or motivation to consider that penalty factor to be Kronecker delta?
Okay, that one, right? Actually, I think they didn't mention it in the paper. I think, I don't know. Yeah. I missed that information too. Or maybe at the later, because I didn't go through until at the end properly. But at the point where they compute things here, they do mention, but I'm not sure taking the Kronecker delta of the Gij, right?
Yes.
Because they for here they look at the use of penalty. The penalty seems like the penalty factor matrix. I'm not sure if it's the property of the penalty factor matrix or to make some equations to decouple or not. I'm not sure that is it. They just mentioned on that.
So that means that if let's say you are choosing penalties that cannot decouple your differential equation, basically
Yes.
you can't solve it.
Yes, correct. It's difficult to solve, it seems. It's still difficult to solve, but I don't see any suggestions maybe to use different methods perhaps if there is a more, that one I'm not sure.
Okay, thank you.
Okay. Hmm.
I have many questions,
Oh, you have many questions? Okay.
but
Sean can help me to answer as well.
you want me to cut down, maybe I'll go to the key ones. Perhaps is okay. As a start, this is different from KY's. Approach.
Uh, Somehow,
Is it
what,
similar?
what what happened? I think it's quite similar because we from KY's work we haven't solved the geodesic equations properly. We just end up until so KY have some penalty as well. They have already the unitary target.
So
But we don't.
in KY, if I remember correctly, is the penalty function is basically a number of 2 qubit gates or something like that, right?
Yes, correct.
Uh, Now going back to your no, perhaps the physical idea behind this.
Mm-hmm.
So uh, you had some Lie algebra, which
Mm-hmm.
you have not really mentioned what it is.
Okay.
Uh, so this Lie algebra will have some Catanza algebra. Okay,
Oh, okay.
okay. So what's the reason of you taking the harmony oscillator kind of thing? Because if you look at, let's say you take SU2, for example,
Uh-huh.
your Hamiltonian in the case of SU2, normally people just take the element of your Cartan-Sum algebra in your
Betul,
sigma.
betul. Can you remind me Cartan sub algebra? So it means that
The generator that commutes with all the other generators.
okay, generators that come in. Okay.
So in this case, you seem to move into the Casimir operator for some reason. So is there a particular reason that you want to go to the Casimir operator, or is it not enough to have your say the
Cartan sub algebra.
Cartan algebra? Because in the case of say the spins, for example,
Uh-huh.
people do use the sigma 3 to be, because that's the diagonal matrix. Okay,
Yes. Mm-hmm.
to use it as a Hamiltonian. Okay, so I was just wondering what's in this particular case, and then it's not particularly clear. One of the things that I wanted to, because you had all these equations which has a single parameter s.
Okay.
Is this a scalar parameter or what?
So the S is so in this case, so they call it U respect to S. Wait, um, because these S appear as a boundary conditions. Okay, I think this S related to the geodesic because you have this distance. Okay, because we solve the geodesic equations, we have some distance. So I'm not sure if it's a scale parameter. Maybe it should be some functions, right? Betul.
Uh, this is the thing I think as no, in order to understand what you have presented. So I really have to think what that represents. So you talk about geodesic distance. So
Yes.
again,
Yes, geodesic distance, correct. It has
geodesic
some
with respect
values.
to what? You know, that's
Oh, okay.
and then now if you take, for example, SU2, of course you can take say, because you have only one element of Cartan-Cell algebra. Let's say you have more elements in your Cartan-Cell algebra, then probably you have to replace your one scalar parameter by some.
Other scale
Yeah.
parameters.
So maybe a vector parameter kind of thing. But again, my difficulty is to be able to understand both from the physical sense and the mathematical sense of what's going on.
Mm-hmm.
So I'm not sure what is no. Even before you talk about the Gij equals to delta Ij.
Okay.
So I mean, where do these things lives on? No, these are things that probably of
Okay. I understand.
the question I would pose.
Okay.
So I'm not sure if anyone has any, no, I have not read the paper, so I do not know. Okay, so
Okay, yeah. I'm actually, honestly, I'm not focusing on the earlier the physical of the S. I just straightforward looking at the maths first. Okay, maybe from my part, I apologize for that. Maybe but it's a good thing.
and no need for apologies.
Well, I'm just
we,
no,
we
maybe
are all we are all trying to learn something. So
yes. So maybe I think it's a good thing because they didn't mention also this penalty matrix following the properties of Kronecker delta. They also have referred to other paper. Okay, maybe also a nice paper. Maybe later on next I can try to work backwards a bit, and then we can come into conclusion. Is that okay?
fine. Okay.
So I don't know. For the parameter S, would it happen to be something from, let's say, your one parameter subgroup?
Yeah, but then it will mean you are picking out a particular subgroup. So which parameter subgroup or that's the thing I was thinking. If you really want to take, say, the Cartan cell algebra, then
Uh-huh.
you probably want to just pick one. You might have two elements of a Cartan cell algebra if you go to, say, SU3 or even SU2 cross SU2 kind of thing. So these are things probably, if there are some specifics of what uh, group or what space one's working with. So I understand it can be general, and then you can look into the specifics later on. But
Yes, correct. I think that's how the paper is trying to do. They go general and then but I have not gone through the details when they discuss the generators.
if I'm not mistaken, Euler-Arnold equation appears in fluid mechanics.
Fluid mechanics. Wait.
I don't know. I mean, I've seen the name before. If I remember correctly, it comes from some theoretical paper on fluid mechanics.
Okay. Let me note down that. Fluid mechanics. So maybe our friends from maths would know it better. Okay. Fluid mechanics. Yeah, before this I never came across Euler-Arnold when KY is still working on his thesis. We just have this geodesic or Lex equation. Euler-Arnold. This is once Chong share this paper only, then I try to look at it. Doctor, so if you have several of S, so it means that, what do you mean? You can have does actually I have also question. Do you have like only S or two parameter scale parameter?
Again, I'm asking of trying to understand rather than because normally if you talk about one parameter, then a scalar parameter for that matter, that you only talk about a subgroup. Okay, so you have to choose that subgroup in order for you to do that. So I'm not quite sure how this works.
Okay. Petro Frere. Okay. Mm-hmm. But okay. Yeah, that one I seen it. I think for specific generators, they also consider only respect to some subgroup, right? But yeah, okay, I take note of this.
You were mentioning also they are also using other oscillators.
Oh yes. Okay, maybe I stop this one and I share the paper and let me stop presenting here and I present again. Entire screen lah. Share. So okay, can you see my?
Hang on, I'm trying to search for that paper. Okay.
Okay, so the first one they discuss several respect to the harmonic oscillator, and then for example, if they want to consider the nonlinear part, okay, so this is one. They have this SP2R Lie algebra. So they
But it's still a harmonic oscillator, right?
yes, but they have this. And then but they talk something about this part, okay? Not contained in the harmonic oscillator algebra. This is the thing that some of them they say the algebra is not exponentiated, cannot be exponentiated. Okay, so I'm not sure why this is different from the earlier, because this is different. 4.5 still is different from the earlier, I think. And the other one, they also consider this is the part where they revisited, okay, and then they use J. Okay, they have also this time evolution operator of the inverted harmonic oscillator.
And they don't provide any physical reason behind all this adoption of
So
this.
far, I didn't go through properly for specific on the example, but maybe I missed somewhere. Let's see here. Wait. From the earlier part before they go into Arnold's, but the idea is they want to. Okay, maybe this is the idea. Wait, no. This is the idea. So the computations complexity target unitary operator. So I think target unitary operators, they consider some groups, okay? So these consider to be in Lie groups. So generate expressions elements. So they only consider harmonic oscillator group, right? So at this initial step, they mentioned here, non-exponential nature of group is already relevant. If the Lie has near, all right. And then the Lie group is generated by, I think most of this is using, if the image of the whole group, the Lie group is called, okay, such as SUN, nilpotent Lie group, such as the Heisenberg group. If the Lie algebra is nilpotent, this one no physical, it's more like properties. So they consider sufficient large set of target unitaries. Tak ada ke? Then they compute the bounds complexity.
Siapa author dia?
Siapa author dia? This one. Satya Chaudhary, Martin.
Okay.
Maybe you can also have a look in that.
So from what I can see, I think this is more mathematically motivated than
Yes.
physically motivated. So perhaps there's some rooms for us to do something about this.
That's why maybe from KY's side, perhaps we can see if it works from KY's unitary operator.
So perhaps okay. I mean, here it doesn't say what group precisely apart from the SP to R thing. Again, if one has to make connection with things that you already know, like KY's work.
Mm-hmm.
You probably need to do like SU2, SU4, something like that. You know. Then anyway, let me try to find that Pietro phrase.
Okay, okay.
This was a long time ago. I think it's a very old paper. He has a huge paper on that equation.
Okay. Petrofre on oil. I know. Maybe I stop recording. This